How should you prepare your data before training a machine learning model? It's a problem that many data scientists struggle with, so let's break it down. Picture this. You are trying to predict who will cancel a certain subscription based on two features. First is the person's age from 18 to 80, and second is their annual income from 20,000 to 500,000. A distance-based model compares numbers directly, so a 5-year gap in age looks tiny in comparison to a $50,000 gap in annual income. The model follows mostly income even if age is equally important. So to fix this exact problem, we adjust our data using something called standardization. Standardization makes different numeric features easier to compare by centering them around 0 and giving them the same overall scale so a model is not biased by a feature's raw size. The first thing you're going to do is find the average of each feature using only the training data and then subtract that average from every value so that the mean becomes 0. The next thing you're going to do is find the standard deviation of that data and divide the already centered values by the standard deviation. Now, each feature has a mean of 0 and a standard deviation of 1, so distances and slope reflect real patterns rather than just big numbers. This is especially helpful for methods that use distances or gradients like k-nearest neighbors, principal component analysis, and logistic regression. The pitfalls here are simple. First, do not compute the averages and spread on the full dataset, because that lets information from the testing set leak backwards into the training set. Instead, compute them on the training split only, save those numbers, and then apply the same transformation to your validation and testing sets. Also know that if you have extreme outliers, those values can still pull your average and spread around and make your standardized values very large in magnitude. If you have many of these extreme values, you might want to consider something called robust scaling instead. Robust scaling tries to achieve the same goal as standardization, but it resists outliers by using the median for the typical level and a robust measure of spread for the scale. Take a look at your training data and work feature by feature. First, find the median of your dataset and subtract that value from every number so the middle goes to 0. Then use a robust measure of spread called mean absolute deviation. Measure how far each value is from the median and then find the average of those numbers. Then divide your center data by this value. Again, when you move to do your validation and test, do not recalculate anything. Apply the same subtraction and division that you learned on the training split. So essentially, we're getting the same result as we would from standardization, but a single strange day in the market or a faulty sensor reading will not blow up the scale. This is particularly useful with financial features like raw dollar amounts, web traffic, or sensor readings where occasional large jumps are normal. All in all, if your data is truly clean and roughly bell-shaped, then stick to standardization. But in most real-world cases, outliers are common and robust scaling is usually the safer choice. Next, let's talk about the normalization strategy. Min-max normalization rescales each numeric feature into a fixed range, often from 0 to 1. Essentially, you take a look at the smallest and largest values of a feature in your training data. You then shift and stretch every value until the smallest becomes 0 and the biggest becomes 1. And everything else falls in between at a proportionate location. This keeps the relative order of the values and fits them neatly into a box that many models and activation functions like to work with, such as neural networks with the sigmoid and tan functions, or just any system that expects inputs in a fixed interval. Now, the main caution is sensitivity to outliers and to future values. If a new value out prediction is larger than any value in the training set, then the new rescaled value will exceed 1. And if it's smaller than any of the training values, it will drop below 0. That's not wrong on its own, but it can surprise parts of a pipeline that assume that the range is strict. A common practice is to clip values back to the chosen range after scaling. As with everything else, always compute the min and max on the training data, save them, and then apply it to the validation and testing sets. This next data management strategy is for categorical data. One-hot encoding shifts a simple categorical feature into a set of numeric features so that the model can learn to work with them. Suppose you have a feature called colors with the values red, green, and blue. A model that accepts only numbers cannot work with words directly, so you decide to assign the number 1 to red, 2 to green, and 3 to blue. However, this can accidentally create a fake sense of order and distance for the model, and we never want to do that. One-hot encoding avoids that problem by creating 3 new features. The first feature is 1 if the color is red and 0 otherwise. The second is 1 if the color is green and 0 otherwise, and the third is 1 if the color is blue and 0 if it's not. Now the model can learn a separate weight for each category without implying that green is greater than red or that the gap from red to green equals the gap from green to blue. But remember, when you deploy a model, new categories can appear. Handle them by sending anything unseen to a separate unknown bucket rather than just dropping them. and only build one hot columns from features seen in the training split. Ever create columns for categories that the model has never seen before. Additionally, if a feature has many categories, one hot can explode the number of columns and slow or even overfit the model, so consider a different encoder. Target encoding replaces each category with a single number that reflects how that target typically behaves for the category. It's compact and can work well with a large number of categories. However, it requires a very careful setup to avoid leaking target information, so it's usually considered more of an advanced option. All of these strategies are about making features comparable and friendly to learning algorithms and doing so in a way that does not leak future data. It's important to note that you usually should not stack two scalars on the same numeric feature. Pick just one based on its data shape and the presence of outliers. Nevertheless, with these strategies, your model stays consistent, realistic, and ready for your machine learning model to learn from it. And with that, don't forget to save this video for the next time you're working with crazy data and follow for more.